Hello Year 10, Mr. Cartledge here, and I'm about to go through your Year 10 science mock to show you what the correct answers were, how you can get those marks, and also a few tips about how to lay out your answers and the sorts of tips and hints that they're giving you in the question as well. As with all of these mocks and exam questions that we do, so much of it comes down to exam technique. So hopefully as we go through this, you'll pick up some of those tips and be able to see where maybe you missed out on some marks. If as we're going through there's a question you got 4 marks on it, obviously don't worry about looking at that question, just skip through the video to the questions where you drop some marks. So we're going to start with question 1, which as is often the case is about atomic structure, as that's where it all begins. So it says here, the question is about atomic structure and elements. And it says, complete the sentences. The atomic number of an atom is the number of what? So just to remind you, on your periodic table, and I've got one here, I'll just slide that across. You are familiar with the 2 numbers of each element. You've got the number on the top, the number on the bottom. So one of these numbers is the atomic mass, and one of these is the atomic number, proton number. So in this case we can use the key, and that will help us to remember which one is which. So the question, just go back to that, it says the atomic number, and actually there's a big clue in here because it says the atomic number, or in brackets the proton number. So the atomic number is that smaller number, and that tells us the number of protons. The mass number is the other number, the relative atomic mass, which on most elements or on all elements is the larger of the 2 numbers. And that number tells us the protons and the neutrons. Question B says, explain why an atom has no overall charge. Use the relative electrical charges of the subatomic particles in your explanation. So subatomic means smaller than an atom. So just a little reminder, what particles do we have? We have protons, which we've mentioned. We've got electrons, and we've got neutrons. So neutrons, a bit like the name suggests, that's neutral, so that doesn't have a charge. The protons, if you're pro something, you're often positive. The p's, remember me going on about matching up the p's, that's going to be a +1. Neutrons, we said it was neutral. So the other one we're going to have is the negative charge of the electrons. So we've got our charges, we've got our different subatomic particles. The question, explain why an atom has no overall charge. So for charges, we're not really interested in neutrons, but we're interested in the protons and electrons. And all atoms have the same number of protons and electrons. So at the moment that is 1 mark, but it's a 2-mark question because the other part says use the relative electrical charges in your explanation. So just to make sure I get that 2nd mark, I'm going to add that in as well. Protons have a +1 charge. Electrons have a -1 charge. And there's my 2 marks. Okay, going down to question C. It says, explain why fluorine and chlorine are in the same group of the periodic table. And there's a big clue here because it says, give the electronic structure of those 2 elements, of fluorine and chlorine, in your explanation. So that suggests, it's a big clue, it suggests that it's got something to do with electronic structure. So let's first just work those ones out. So we're looking at fluorine and we're looking at chlorine. So I'm going to pull across the periodic table. We've got fluorine here and we've got chlorine here. If we're looking at the electrons, we need to look at that smaller number. So fluorine has 9, chlorine has 17. Okay, so I'm just going to write that down in my answer. So fluorine, F of fluorine, that has 9 electrons, and chlorine has 17 electrons. It says electron structure, so how do those electrons fit into the different rings? You might remember in our atom, we've got lots of different rings, lots of different shells. The number of electrons that can fit in those shells, do you remember the rule 2, 8 and 8? So therefore, fluorine, starting from the first shell, the inner shell, its electron structure is 2, 7, adds up to 9 in total, and chlorine is 2, starting from the centre, then go to the next shell, so that's 8, and then the next shell, 7. What do we notice about those electron structures? They both have 7 electrons in the outer shell, they're both the same number. And in fact, if I pull back the periodic table, just a reminder, the group number is this column, and if we look, they're in group 7, and that 7 matches the 7 electrons in their outer shell. So they have the same number of electrons in the outer shell. 2 marks. They give you the clues in the question, points in the right direction to think about or to know where to begin to answer the question, to what to think about. Let's go on to the second part of 1. So cross over onto D. It says, the diagram shows the electronic structure of an atom of a non-metal. What is the chemical symbol of this non-metal? So you can see we've got our nucleus, we've got the shells around that nucleus, and in those shells are the electrons. So what I could do, I just count those up. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So in total, I've got 16 electrons. Let's get that periodic table back. 16 electrons. Remember, the smaller number on the periodic table is the number of protons and electrons. We're looking at non-metals, so somewhere over here, there is 16. So our answer is sulfur. And that's question 1. So moving on to question 2, and this one looks like it's going to be about a practical. It says at the top, a student studied the effect of temperature on the rate of reaction between hydrochloric acid and sodium thiosulfate. So just a reminder, the rate of reaction, what we're talking about here is, if you like, the speed of the reaction, how quickly does that reaction take place. And you might remember this little setup. So we've got the cross, we're going to put the flask up on top of that cross, and as the reaction takes place, the cross disappears. So you will all have done this in class. You'll look down from the top, look through the liquid, and wait to see until you can, or time how long it takes for that cross to disappear. It says the student mixed 50 centimeters cubed of sodium thiosulfate solution and 5 centimeters cubed of hydrochloric acid in a flask. The flask was placed over a cross. The student timed how long after mixing the cross could no longer be seen. So a little reminder of that practical that you will have done. Question A, part 1, is balance the chemical equation for this reaction. And this one is a bit of a beast, isn't it? There's a lot in here, a lot of different elements, a lot of numbers to try and work out. So if we're balancing, what we're trying to do is make sure that all of the atoms on the left end up somewhere on the right. So what that means is we've got to make sure we've got the same number of each type of atom on the left side as the right hand side. There's a lot of atoms to look at, so it'd be good to have a bit of a technique. The way I like to do it, the way I think it's easiest, is if you come to, or start with something that looks a little bit harder and finish with an element that looks a little bit easier. So if you see on the right here, S all by itself, that's going to be kind of the easiest element to have a look at. So I'm going to leave S towards the end. And S is over here amongst these guys. So what I might do is I might start by looking at the HCl. So let's have a look at that HCl first, see what we can work out with those. So H is first. Well, I've got one H on the left. I've got two H's on the right. Remember, the small number tells us how many of that particular type of atom there are. We start each new element whenever we get to a new capital letter. So I've got one of these, I've got two of these. Now what I can only do if I'm balancing, I can only add in large numbers in front. So what I'm going to do, I'm going to have more hydrogen on the left. So I'm going to add in a big 2. You cannot change any of those little numbers. So I've now got 2 hydrogen, 2 chlorine. Let's look at the hydrogens. 2 hydrogens, got 2 hydrogens, they're fine. Look at the chlorines, 2 chlorines. Well, that doesn't match our chlorines on the right. So I now need a big 2 in front of there. My HCl are sorted. Let's look at the other substance, S's. S was one I was going to come to last. So let's have a look at that now. I've got a bit of information in there. For 1 sulfur, here I've got 2. Oh, but I've just missed out. I haven't just got 1 sulfur, have I? I've actually got 2 sulfurs. 2 sulfurs in total. Here I've got 2 sulfurs. Perfect, they're okay. Let's just make sure on those other atoms. Na I've got 2. I've now got 2 in total on the right. Oxygens I've got 3. Got 1, 2, 3 on the right. So that's the only thing I need to do. Part 2 says, what causes the cross to be seen no longer? So if you can't see through the flask, the reason you can't see through it is because a solid has appeared and is blocking the light, it's opaque. If we look at the equation, they're telling us about each of these different substances. We've got AQ, so that's the solution. So in 2 solutions together, we're forming another solution, forming a liquid, forming a gas, and we're forming a solid. This solid is given a special name. It's called a precipitate because it's a solid formed from 2 solutions. So what causes the cross to be seen no longer? It's a solid, it's S. Let's just have a quick check on the periodic table. What was S? Because I can't quite remember. Quickly have a little scan. You might be able to spot it before me. There it is. We looked at it earlier actually. Sulfur. So I'm going to put sulfur in there as my answer. Part B is going to have a look at some graphs. So I've got one graph down here, which is a simply showing the time for the cross to not be seen in seconds, temperature. So as the temperature is increasing, the graph shows that the time takes less, which means that sulfur must be being produced quicker. So the reaction rate actually speeds up as the time is taking less. Let's go on to the questions. What do the questions ask me? Oh, the question asks me, what effect does temperature have on the rate of reaction? So the temperature I have on the rate of reaction, well, I can't just write, which would be tempting, would be to say increases rate of reaction. I can't do that. That would be 0 marks because I've not said what is it about the temperature. Is the temperature increasing? Is it decreasing? What I've got to say instead is as the temperature increases. Make sure in your answer you're mentioning both parts, the temperature and the rate of reaction. So if I'm doing any graph work, I'm going to mention both of the axes. I'm going to mention the temperature, and in this case it says the time, so that time corresponds to the rate of reaction. Explain why temperature has this effect. So if you remember, reactions occur as two particles come together and they collide. When we talk about successful collisions, you may have heard me using a boxing analogy. You've got to hit the opponent hard to have any kind of effect for it to be successful. There's no point in just tapping them. That's the same with our particles. They've got to collide with a lot of energy for it to be successful. And we also, the other phrase we like to use is frequent, or the frequency of collisions. How quickly are those particles colliding? How often are they bumping into each other? So as temperature increases, what's happening? So I'm going to bullet point this to make it really clear to myself where I'm getting those marks. So as temperature increases, what happens to the particles? As temperature increases, the particles move faster. What happens as they move faster? For a second mark, the particles collide more frequently. Okay, so collide more frequently, that's one of my key phrases or key ideas I've mentioned. It's only 2 marks, so actually that gets me 2 marks. But what I could also add in there is that the particles, or I could say more collisions, are successful. Which is that second part. I don't need to say that because I've already got my 2 marks, but in a 3-mark question I would need to include that as well. That's question 2. So moving on to question 3, and we've got another graph, another bit of analysis that we need to do about a practical. So looking from the top, it says a student investigates how the concentration of an acid affects the rate of reaction. This is the method used. They put a 3 centimetre piece of magnesium ribbon into a conical flask. They add 50 centimetres cubes of 0.5 molar hydrochloric acid to the flask. Remember, that tells us the concentration. They collect and measure the volume of gas produced at 10-second intervals, and they repeat at different concentrations. So they might start with 0.5, but they're going to change that concentration each time. They're using the same length of magnesium ribbon and the volume of acid. The students' results are shown below, so let's have a look at those results. So here's the graph. You can see all of the graphs are going up because we're measuring a gas being produced. The 2 molar is going up the fastest, 1 molar is kind of in the middle, and the 0.5 molar is going up the slowest. The graph is going up the slowest. They all finish at the same point. Let's have a look at the questions. So question A says, how do the results show that increase in the concentration of acid increases the rate of reaction? And you must use data. You must use data. So if you don't do that, you're not going to get your mark from the graph in your answer. So let's have a look. We said that the 2 molar increases the fastest. So we could say that let's bullet point this. 2 mole per dm cubed. Let's keep with their language. 2 moles per dm cubed graph increases the fastest. And remember, when they go flat, that's when no more gas is being produced. So that suggests the reaction is finished. So the 2 molar reaction finishes first. So I could add that to my answer. 2 moles per decimeter graph increases the fastest and finishes. Oops, I'm just going to change that to the reaction. This is not the graph. The reaction finishes first. Notice in the way I'm saying this, I've said the fastest and I said first. So I'm comparing the 2 molar to the 1 molar and the 0.5. Let's get some data in there. So I want to say that 2 mole per dm cubed finishes at 20 seconds, and that, let's go for 1 mole per dm cubed finishes at 41 seconds. That's part A done. Let's have a look at the next page. Part B. Explain why the rate of reaction explain why the rate of reaction changes as the concentration of acid changes. You should answer in terms of particles. So a bit similar to that last question about temperature. The key phrases, can you remember what those key phrases were? Key phrases: frequent collisions, something to do with how frequent those collisions are, and successful collisions. They're going to be the 2 things that are determining the rate of reaction. So, as the concentration increases, what is happening to all of the particles? Well, I'm going to draw, I'm going to draw a gas here, so it's not going to be quite fair. And my boxes aren't quite the same size. That wasn't very good, was it? But let's imagine 4 particles in that box. In this box, I've got more particles in a smaller space. If I've got more particles, not a smaller space, I've got more particles in the same space, they're going to collide more frequently. That's what's happening when we increase concentration. We're kind of cramming in, we're forcing in more particles into the same volume. So let's put that down. That could be my first point. At a higher concentration, there are more particles, not necessarily in total. What's important is in the same volume. All right, I've got to, this is where lots of people miss that mark, I've got to match it to the volume. If I had a big box with more particles in there, those 2 are going to have a similar rate because the distance between the particles and how frequently they're going to collide is not going to change. So it's more particles in the same volume. Second point, what happens? So more frequent collisions occur. And my last point, so that's my frequent collisions. Does the success of the collisions, does that change? Well, not if I'm only changing the concentration. If I'm only changing the concentration, that doesn't affect the success of the collisions. So I don't have to worry about that one in this answer. But what I could add in here is just to say that the reactions occur when particles collide. Now I've made my 3 points. Now I can get those 3 marks. Right, question C. Student A said that the final volume of gas collected was lower for concentration of 0.5 moles per dm cube because the reaction had not finished. Let's just go back and have a look at that statement. So we're looking at the 0.5. So here's 0.5. It's coming up, it's coming up, it's coming up, coming up. Doesn't ever quite become flat. So it doesn't finish. Right. So student B said it was because all of the acid had reacted. Describe further experimental work the students could have done to find out which student was correct. So let's have a look at that graph. What would be the most obvious thing to do? They could repeat that same experiment rather than stopping at 60 seconds. Well, why don't they just keep going for a bit longer? And then you'll see whether the reaction has finished or not. So, repeat experiment. And leave for longer. And then we could say which one's correct. Is it going to be student A or student B? We could say if more gas continues to be produced, then student A is correct. That's question 3. So on to question 4. We're nearly there, just 2 pages to go, and this was really juicy. There was lots of good marks available in this question. We're back to those atoms, aren't we? Crucial, and they get you so many marks. Got to know them inside out. It says here, sodium is a reactive element. Complete the diagram to show the electronic structure of a sodium atom. So we're looking at those electrons again, and we're looking at the sodium atom. Right, so I'm going to need my periodic table. So I need to find sodium. Sodium's here. Was it the big number or was it the small number I need to look at? So I'm looking at the smaller number. That tells me the number of electrons and the number of protons. And I'm now interested in the electrons. So it was 11. So I'm going to put down 11 electrons. Remember the rule from earlier? 288. So let's start in the centre. Put 2 electrons in. Next shelf it's 8. I've used 2 already, so that's another 3, 4, 5, 6, 7, 8, 9, 10. I've got 1 electron left. Pop him on the outside. 2 marks. Question B. Sodium reacts with chlorine to form sodium chloride. Explain how in terms of electrons, atoms, and ions. So sodium is going to react to form an ion. If you remember, what was the difference between an atom and an ion? An ion has a charge, So we're going to get onto that charge in a moment. Explain in terms of electrons, atoms, and ions. So, what is the problem with these electrons at the moment? Sodium atoms are really reactive because they've only got that one electron on the outside. Remember, atoms become stable when their outer shell is full. So, how could this atom get a full outer shell? Well, shell 3 needs another 7 electrons, or, and it'd be a bit easier, wouldn't it? It could lose 1 electron. So let's have a look at what we could put. Sodium loses 1 electron. Right, what's going to happen to that sodium atom now? Remember, if electrons are negative and it loses that negative electron, we get left with a positive ion. Remember, protons are positive, electrons are negative, -1 plus 1. So if I've got protons, at the moment I've got 11 protons, I've got 11 electrons, gives me a charge of 0. But if I lose an electron, I then have 11 protons, 10 electrons, a charge of +1. So sodium ions have a charge of +1. That's about my sodium. Question was 4 marks though. So where am I going to get those other 2 marks? Well, I need to also talk about the chlorine. So chlorine, I haven't drawn the atom, but I need to know what happens to chlorine as well. I could quickly check my periodic table and do the same process again. It's got 17 electrons. So Cl equals 17 electrons. Those electrons are going to be 2, 8. That gives me 10 electrons. So the third shell is going to be 7. So how many more electrons does chlorine need to become stable? To get that full outer shell, it needs 1 more. So I want to bullet point this still. You can bullet point the whole time, that's absolutely fine. I find it makes it much easier, so I like to bullet point. Chlorine is going to gain 1 electron. And so what's going to happen to the charge? Chlorine ions have a charge of -1. Okay, so I've got a positive ion, I've got a negative ion. That's my 4 marks. If you had said ionic bonding, which is when you get attraction between the positive and the negative, that can also get you a mark. If you say about full outer shells, that will get you a mark, but you're not going to get the full set. For the full 4 marks, you've got to mention each one in turn. And we've used our terms, electrons and ions. Okay, last question, going over the page, on to question 5. Question 5, right, so here we go. It says the diagram shows part of an ionic lattice of a sodium chloride crystal. Complete the spaces in the table to give information about both of the ions in this lattice. There's a big clue in the question because it's telling me about the different ions that are present. So it says sodium chloride, so I'm going to use that in my answer. Sodium and chloride. What's the charge on a sodium ion? Well, it is positive because it is a metal, because it only has one electron on the outer shell. So I'm going to give it a +1 sign. Chloride, I'm going to give it a -1. 2 marks. They're giving me lots. Lots of students forgot that it was chloride and wrote chlorine. Remember, when non-metals bond, we often change the end of their name from an "ene" to an "ide" because they become a charged ion. So when it becomes charged, we change it from chlorine to chloride. Part 2. When it is solid, sodium chloride will not conduct electricity. However, molten sodium chloride will conduct electricity. Explain this difference. So if we go back to the diagram is showing solid sodium chloride. How do I know that? Because do you see how they're on neat rows the whole time? And it looks like they're kind of fixed into position. They're kind of being tightly held in position. So as a solid, those particles are unable to move around. For something to conduct electricity, there's got to be the opportunity for those charges to move. So how can we put that down into an answer? When solid, charged ions are fixed in place and cannot move. When molten, charged ions can move. Is there a way to remember this? It's a bit of a tricky one, isn't it? I like to always think, if I'm thinking about electricity, I like to think about a circuit from my physics. And if you remember, in a circuit, you've always got the electrons flowing around the diagram, flowing around that circuit. The electricity is those charged electrons moving. They've got to move. If they can't move, can't conduct electricity. Circuit doesn't work. It's the same situation in chemistry. So when they're solid, the charged ions can't move, can't conduct electricity, they have to be able to move. Final question. Complete the sentence. Sodium chloride conducts electricity when it's molten and when it is... When else could those particles move? When it is a solution. You could have, which is a little bit ridiculous, a gas, because the particles can still move. And you could even say, when it is a solid, it will not move, which seems ludicrous, because that's what they've just told us. But you could also have that as well. Excellent. So I hope that's been really helpful, and look forward to seeing all of your wonderful corrections and that you've been using this video in our next lesson. Great job.